As I mentioned at the end of the previous video, this video is just going to be going through a whole bunch of definitions and theorems as they relate to sequences. And I'm going to start here with the limit of a sequence. And it's very similar to when we studied limits before. The limit of a sequence says that if we can find an n value large enough, all values of the sequence are going to be within a predetermined distance. We'll call that epsilon of a certain number. And if that holds true, we call that number the limit. If there is no such number, we say the sequence diverges, but when there is a number, it converges to that number, whatever that number L happens to be, the limit. So I've got a picture here that shows a representation of a limit in two ways. The one is with just a number line, that's on top here. So you can see we have different values of a sequence, and once we get out to a certain point, all those sequence values are going to be within epsilon of this limit L. That's one visual way to represent it. The second one is in the xy plane, where the x values are going to be the values of the index number. The y values are the actual value of the sequence term. And once we get out to a certain point, again, once we get beyond a certain value of the index numbers, all of the sequence values are going to be within that band, epsilon units above or below that limit L. On the next page, and I am not going to read through these, but it goes through how you can use that limit formula to show that the limit of 1 over n as n goes to infinity is 0, and we will make use of that later. And if your sequence is just a constant, k, the limit of that is going to be k, because the values are not changing. If you have a sequence similar to the one that we did in the example with the ones and zeros, where you're going between two different numbers, that sequence diverges. It's never going to go to one number because it's bouncing between two of them. And again, you can read through those in a little more detail. I just want to go through it quickly. Now, I mentioned before, not all sequences are going to converge to a limit. Some of them diverge. And if the sequence terms start to get larger and larger and larger, we say they diverge to infinity. If they are getting smaller and smaller and smaller, we say that they diverge to negative infinity, and that will happen sometimes. We keep going, and there are a lot of theorems and terms in this section. The first theorem here that we come to says that if you have two sequences and they each have a real number limit, you can add, subtract, multiply, and divide those limits. You can even, in number 3 there in theorem 1, you can even multiply the limit by a constant. The second theorem is called the sandwich theorem, and this one we'll make use of in an example later. It says if you have a sequence b sub n, and it is sandwiched between two other sequences, here we call them a sub n and c sub n, so that for all values of n beyond some given number, that those b sub n terms are going to be sandwiched between the other two. If the sequence a sub n and c sub n both have a limit of L, b sub n will too. Okay, so you're sandwiching between two other sequences. And underneath it is an example of how this works, and I will go through an example of this as well. But because the sequence 1 over n goes to 0, we can use that to show that cosine n over n goes to 0. 1 over 2 to the n also has a limit of 0. Negative 1 to the n times 1 over n goes to 0. And then if the absolute value of a sequence goes to 0, then that sequence a sub n will also go to 0. So that's just using that sandwich theorem. And again, we will come back and do an example of this later. If you go to the next page, we've got a few more theorems. The first one is the continuous function theorem. This says if a sub n is a sequence and it goes to a limit L, and f is a function that is continuous at L and it's defined at all values of that sequence, then we can basically apply that function to the sequence and its limit will be the function value of L. Theorem 4 is very related. It says if f of x is a function defined for all x greater than or equal to some value n sub naught, and a sub n is a sequence where a sub n equals f of n for all values of n greater than or equal to some value n sub naught, then the limit of the sequence is going to be L whenever the limit of the function is also L. So we're able to define sequences in terms of functions. Theorem 5, this is the one that I would suggest highlighting, put a post-it on it. We will come back to this in later sections in chapter 10. This gives 6 different sequences and what they converge to. In a minute, we'll use, I think, 1, maybe 2 of these in an example. But like I said, in later sections, we will come back to some of these. So this theorem 5 is one that you want to somehow mark so that you can easily come back to it. Underneath that, I've got a recursive definition. We're not going to deal with sequences that are defined recursively very often in here, but a sequence that's defined recursively says that it gives you the initial term or possibly the initial terms and then a formula to get later terms from that initial term. So for instance, it might give you something like this. A sub 1 is 3, and then it might say a sub n is a sub n minus 1 plus 2. So if a sub 1 is 3, a sub 2 is going to be defined as 3 plus 2 or 5. Then you could say a sub 3 would be 5 plus 2, 7, and so on. That's a recursive definition. And again, we're not going to see that too often in here. Beneath that definition, I've got the definition of sequences that are bounded. And if there is a number such that the sequence values are all less than that number, we call that number an upper bound. The smallest of the upper bounds is called a least upper bound. And similarly, if there is a number that is lower than all of the sequence values, we say that is a lower bound, and the largest of the lower bounds is called the greatest lower bound. If a sequence is bounded both from above and below, if it's got an upper and a lower bound, we say that it is a bounded sequence. And then last 2, and then I'll end this video and we'll look at a couple more examples. Definition of a non-decreasing sequence. It's a sequence where all terms are greater than or equal to the term before them. So the terms are not always necessarily getting larger, they're just never getting smaller. And then the flip of that is a non-increasing sequence where all terms are less than or equal to the term before them. If a sequence is non-decreasing or non-increasing, we call it monotonic. And that leads to theorem 6, which says if a sequence is both bounded, that means you've got that upper bound and that lower bound, and it's monotonic, that means it's non-increasing or non-decreasing, then the sequence converges. Now, on the next video, I'm going to go through some examples. I'm not sure, there's 5 examples. I might try to go through all 5 of them in one video because they don't take too terribly long. But we're going to go through and look at some different sequences and look at which ones converge and which ones diverge. And I'll show you how to find the limits of the ones that are convergent.